I really appreciate the invitation to come speak with you. This is actually my first trip here, so I'm going to assume it's not always this cold, but yeah, sometimes it's colder. Great. Well, I'm glad I picked a nice warm day to come. I had a fascinating discussion with several of you during the day, and it occurred to me that what I'm going to present here really has nothing to do with any of the questions you guys asked me today. So hopefully what I put together here is interesting. I know quite a bit about Sean's background. We've interacted quite a bit with some joint work that we're working on. And so what I wanted to do is pick topics that I thought would complement what a computer scientist would know and would approach the problem. And so I really focused in on the grid and talking about the grid. So I'm really not going to spend any time talking about cybersecurity of the grid, even though I've personally been involved in cybersecurity matters related to electric power grid since 1994. And there's a lot of interesting things here to talk about. What I wanted to do is talk about the grid and some of the trends going on in the grid. I'll hit on one of my favorite topics to talk about. That's the 2003 blackout. So I've got some slides on that. And where the grid is going with what we call smart grid technologies. So I'll define that and talk a little bit about that. And I have some comments thrown in about resilience. And when you think about the reliability of the grid, we all depend on the grid. We all know that. And reliability of the grid is very important. But one of the things about the grid is the consequences of losing the grid. If you lost electric power, the consequences of that increase with the amount of time it takes to recover the grid. And so the time to restore is a really key element. And that's wrapped up in this concept of resilience. But I also think resilience is deeper than that. It's also having a grid that's either fault tolerant or quick to recover, regardless of the threat scenario that you paint. And so regardless of how the grid is interrupted or disrupted or attacked, the resilience concepts kick in and either help you mitigate the event in the first place or do a better job with restoration. So I've got some thoughts about that. So we'll try to zip through this. I really have a lot of materials that I packed in. I'm assuming about an hour time-wise, and so and we can save some time for questions. Unfortunately, I don't want to take questions as we go because then I will then have no hope of getting through my stuff. But this is essentially my outline that I just described, and my caveat here is I'm just scratching the surface. So don't feel like, or don't be prepared to become experts in grid resilience in the next hour, but I'll try to offer up some thoughts and perspectives. One of the things I really like about working on the grid is it's a very complex and challenging problem. And a couple of years ago, the National Academy of Engineers put together what they considered the 20 most important engineering achievements of the 20th century. It was kind of reflecting back on the 20th century at the turn of the century, turn of the most recent century. And they picked the widespread electrification of society as the #1 engineering accomplishment in the 20th century. And it's really daunting when you think about some of the other things on the list, you know, like airplanes, you know, the internet, number 13. You know, there's a lot of things on this list that are really important accomplishments, but they grabbed the powering our people as #1. I think that's pretty cool. And I also like to think of this as a big machine. So we're here in New Hampshire, and if I stick a meter in the wall and measure the frequency of the grid, it's close to 60 hertz. May not be exactly 60 hertz, but it'll be close to 60 hertz. As the frequency varies through the day, you know, based on how much load, how much generation is on, but the utility companies kind of manage that 60 hertz. But what's cool to think about is if I call up a colleague down in Florida and say, hey, measure and tell me what the frequency of the grid is right now. It's the same number as it is up here. It's one grid that we're all connected to in the Eastern Interconnection. So what I have on this map is showing how the grids are split into different grids. The only way to move power between these grids on this map is through a DC connection. So you can take your alternating current, convert it to direct current, and then reconvert it back to alternating current. Each of these grids I have on this map, they nominally run at 60 hertz, but they might be slightly different depending on what's going on at that particular moment in time. Each of these grids runs as a single machine. So the example I was talking about earlier were New Hampshire and Florida. All of the motors, generators, and synchronous machines, and every part of that interconnection is running at the same speed. And it really does behave as a big machine. The Eastern Interconnection is the largest machine, or largest grid of any grid in the world if you measure it in terms of megawatts. If you measure it in terms of size, the Russian grid is larger in terms of geographic size. That's the largest one in the world if you measure it in miles. But measured in megawatts, the Eastern Interconnection is the biggest. You'll notice a couple of outliers that we have. We have the ERCOT interconnection, and that's within the state of Texas. And we have the Quebec interconnection, and that's the province of Quebec. And so Quebec is like Canada's version of our Texas. They like to be independent. This is an example of a control room that runs this grid. There's roughly 140 of these rooms across North America that run our grid. And so these are the larger utilities. This particular picture is from the California Independent System Operator. And so these 140 control rooms coordinate their operation together and manage this machine that we call the electric power grid. The other thing is you can think about this infrastructure and slice it out different ways. Obviously, the power needs to be generated. Roughly, it's a diminishing fraction actually, but about 50% of our electricity is produced by coal. We have a growing percentage of our energy is produced by natural gas, and that's primarily because the gas prices have gotten so much cheaper. About 20% of our energy is nuclear, and about 10% of our energy is hydro. And then we have a growing fraction that's still relatively small from wind and even less from solar. And then the generation is brought from where it's generated to where it's consumed through transmission. Now, the terms transmission and distribution, those might, to a layperson, those might sound interchangeable, but they're not in our industry. Transmission refers to the high voltage system that interconnects the substations, and that's the mesh networked multi-state high voltage system. The distribution is from the substation to the customer, and so that's generally a lower voltage. So typical voltages for transmission, these towers here that you're seeing are 230,000 volts. But 345,000 volts is common, 500,000 volts is common, 765,000 volts is not so common, but is in use in the US. Distribution voltages are typically in the order of 12,000 volts. So just to give you an idea of the size there. And then all of that is meaningless unless you serve a load. And so in the US, roughly about a third of our consumption is for industrial customers, a third is for commercial customers, and a third is for residential customers. Now, I mentioned substations earlier. So substations is the point of demarcation between the transmission and distribution, but they're also incredibly important because this is the part where the system is actually controlled. So that control room picture I showed earlier, they have telemetry coming from the substations. And so the monitoring the status of the system, this is where the protective relays are located, the circuit breakers, so if there's a problem or a fault on a line, this is where all the equipment is that isolates that line, de-energizes it, and keeps things from becoming damaged. And then the substations also provide the nodes of that interconnected mesh transmission network. So substations are really important. And from a control systems perspective, they're also very important because this is where all the data comes from. So the data that's used to provide the operational support at the control center comes from the substations. There's different, I'm not going to get into a whole terminology of the different types of control systems, but the most important one from the electric utility standpoint at the transmission level is what we call SCADA, and that stands for Supervisory Control and Data Acquisition. And the idea with SCADA is it's gathering data from the substations and bringing it to the control center, and then that's used to create real-time computer models of what's going on in the control area or the grid that control room is managing. And then that's used to develop contingency analysis to support operational decisions. And I'll get into more details of that later. And then if there needs to be a change to the topology, or if there's a need to manage the system, for example, bring a transmission line in or out of service, or bring a generator up or down, or those types of things, that is also communicated through that SCADA telemetry. Oops, wrong way. So here's an example of a substation that's not in operational order. So this is a picture 6 weeks after Hurricane Katrina. It's from Plaquemines Parish. Down in Louisiana, parishes are like counties. And so this is south of the city of New Orleans. And when this picture was taken, again, it was 6 weeks after the storm, there was 0% recovered customers with power in that whole entire parish. And that was a big devastation and a big effort to bring that infrastructure back. And as we drove down and were assessing the damage of the infrastructure, we were driving by miles and miles and miles of transmission distribution cables just laying in the side of the street. And then we'd come across substations like this that were just completely demolished. The damage here was the storm surge and the water effects that wiped it out. This wasn't wind damage, this was water damage. So the grid operates really fast. One time I quipped that it operates near the speed of light, and then I was quickly corrected by somebody that was keeping me honest. So okay, 1,000 miles per second. That's pretty fast. Not the speed of light, but 1,000 miles per second. That's roughly the speed of the electromechanical phenomenon. So when I talked earlier about New Hampshire and Florida being connected, well, if something happens in Florida, that'll ripple through the entire interconnection, but it takes 1,000 miles per second for that to propagate through the system. That's faster than you can manage from a human perspective, right? So this system is operating very fast. If a power line trips, if a transmission line trips, if something happens to the system, you have to have pre-positioned the response of that without sort of coming up with that plan as it's happening. So this is done through this process of contingency analysis. The shorthand of it is we refer to it as n-1. And the idea there is you have n elements in the system, and you're going to analyze what would happen if any of those elements were to go away. What if this power plant trips? What if that power line trips, transmission line trips? What if this happens? What if that happens? And so you come up with a list of credible contingencies, you analyze those, and then you make sure that if any of those things happen, you would have a stable response. And then you pre-position the grid at all times to be what we call n-1 compliant. Now that -1 is important because you can always be creative and come up with, well, what if this and this and this and this happened? Well, then your grid would fail. So you have to draw the line somewhere, and the idea here is that you refer to these as credible contingencies. So there's a little bit of a, people argue with how sophisticated the science is in terms of really the risk management process of determining what's credible and what's not credible. There's a lot of papers written about, coming up with stochastic and probabilistic methods for understanding what you need to plan for. But the bottom line is that it's a little bit more sophisticated than just looking at single elements, because sometimes there's a dependency involved. There might be parallel lines that share a right-of-way. And so one thing could take out both of those lines, and that would be considered a credible contingency. But they're given different classifications. So in WEC, that's the Western grid, they've defined 4 different levels of contingencies, category A, B, C, and D. And then they're defined with the amount of likelihood that each one of those is likely to happen, and then the acceptable response based on if this happens, then this is the acceptable response. So for example, category A contingency is a loss of a single line or loss of a single power plant. Well, you wouldn't want to be shedding firm load as a result of that. You'd want to have enough reserve margin to handle that. So that's how that works. A category D, an example of that might be a loss of a complete substation with all the lines in and out of it at the same time. And acceptable response is no cascading failure, but you can shed load if that happens. So those are the types of things. And then in order to accomplish this, there's different kinds of reserve margins that the utilities have. They have operating reserves. That's the ability of a power plant to quickly come online. There's spinning reserves. That's a fraction of your online generation capacity that's available to pick up instantly, or relatively instantly, if it's needed. So it's online and running, but it's not deployed or committed. And then there's also a lot of planning studies that are done to set the limits on safe system operation. And so a lot of computer models that are used, offline planning studies and real-time operational studies. This is all done to minimize the likelihood of a cascading failure if something starts to happen. So you want to stop these cascading failures. So I'll take a quick aside here, and this is important from a resilience concept. The topic is under-frequency load shedding. So earlier I mentioned that you can plug in a meter in the wall and you measure the frequency and you can see that it's close to 60 hertz, but may not be exactly 60 hertz. If it's above 60 hertz, what that's telling me is that there's more generation than supply and the system is sped up. And what the utilities are doing at that moment is their automatic control systems see that, and they're backing off the amount of generation. So the amount of fuel going into some of their load following power plants are reducing. They're reducing their generation. They're going to eventually bring that back to 60 hertz. And even if it's an excursion that goes way above 60 hertz, those automatic controls will come in place and bring it back to 60 hertz. And if it's so extreme that some power plants might have to trip on overspeed protection so that the turbines aren't damaged, that's not that bad because it's starting from a position where you have too much supply already. So if you lose a power plant, that's not the end of the world. Well, think about the opposite now. What if it's low frequency? I'm measuring low frequency. The power plants are being instructed to generate more, and you're trying to put more power onto the system to bring that system up. But if it happens so fast or so extreme that you have to trip a power plant on underspeed protection, the shaft and the turbines are running so slow that they might damage, and so they have to trip on underspeed. That's a very critical situation because you're already generation deficient. And so you're going to go into cascading failure if you start tripping power plants on under frequency. So in order to save the grid, utilities have deployed under-frequency load shedding. So these are automatic control schemes in substations. They try to choose feeders that don't have critical loads on them. They'll skip feeders that might be serving a hospital or whatever. But they'll pre-plan which load are we going to shed in an emergency situation. And they're just automatic relays, no communication to them. All they do is they just measure frequency all day long. And if it goes below a certain threshold for a certain amount of time, they're pre-programmed to drop load. And that's intended to bring the frequency back up so you never want to trip a power plant under frequency. So that's a great system that's put in place where it doesn't matter what the scenario is that got you there. The system is there to save the system. The under frequency load shedding scheme is there to save the power grid. No matter how that situation happened, it's going to act automatically to bring things back to a stable equilibrium. Another example of extreme situation is what we call black start and black start restoration and black start restoration planning. This is the concept of recovering after a blackout. A lot of large power plants, particularly big coal plants, for example, you can't just walk up to a coal plant and say, okay, turn it on and start generating power. It needs off-site power in order to run the pumps and the motors and the fans and to get the boiler going and get the water circulating and get the turbine moving. So it needs off-site power in order to operate. Nuclear plants need off-site power, coal plants need off-site power. So what do you do if you have a complete failure of the grid and you can't start any of your power plants? Well, you need certain power plants, maybe a hydro dam or something that's easy to get going. You use that power then to feed your other power plants, and then you use that power then to start bringing your load back on. It's a very complex process here that you need to orchestrate, and it's more complicated because often utilities will share these resources amongst them. So it may not be that one utility has all these resources themselves. They might need to rely on their neighbors to get their system back up. And this was learned the hard way when we've had some blackouts in the past where this planning wasn't complete. So all of this is done with an eye to these priorities I have up here. It's always important. Safety of your electrical workers, but also the general public is very important. So you don't want a power line, for example, to get so heavily overloaded that it heats up and sags and gets down into where it can kill people. The other thing is the next priority is protecting the equipment from damage. So if you have something that's an off-normal situation, you want to trip it, let it recover, and then bring it back as opposed to running to failure. Third is maintaining the reliability of the bulk interconnection system. And then fourth is once you've accomplished 1 through 3, squeeze as much profit as you can out of the system. And I would argue that oftentimes when we have blackouts, it's when 3 and 4 get swapped around. I'm going to skip this slide, but this just gets into more of the history of how we got to where we are. My punchline on this is that with the introduction of computers, the planning of this has gotten a lot more complex, and we've been able to run with thinner and thinner margins than we have in the past. All right, so we do all this to prevent blackouts, but blackouts happen. So this is my hit list of all my favorite dates in history. So the 65 blackout, a lot of lessons were learned on that particular day. A lack of black start plans, for example. Simple things like having an emergency backup generator for your control room. Yeah, that's a good idea. Don't need flashlights. So a lot of things came out of that. But probably one of the most fundamental things that came out of the 65 blackout was the formation of an organization called NERC. NERC, it's shifted in the past few years, but its new name is the North American Electric Reliability Corporation. And what NERC was back then is an industry organization to come up with agreed upon rules of the road. So all of the utilities that interconnect with each other would have a common set of requirements that they would all operate to, planning requirements and operational requirements. That organization was formed after the 65 blackout. 77 blackout is interesting from my perspective because if you notice on the chart there, it was a smaller blackout, smaller footprint, fewer number of people affected, but it was actually a more expensive blackout than the 65 blackout. 77, things in New York weren't as much, the society wasn't really well behaved on that day, and they practically burned the city down and with the looting and rioting and things like that, whereas 65, people are pretty well behaved. So the cost of these events don't necessarily relate to the number of people affected and the size of the blackout. 82 was a windstorm, knocked one set of lines into another. 89, that was a solar storm, geomagnetic disturbance, affected Quebec. 94, the January 94 was an earthquake. December 94 was a relaying error. July 2nd was a relaying error, another relaying error in a different set of lines. What's not shown on here is July 3rd. July 3rd, the same set of events started to happen on July 3rd that happened the day before, but because the operators were in the control room were so keyed up, it's like, oh crap, it's happening again. They immediately shed a bunch of load in a particular city and it stopped the cascading sequence in its tracks. And so we call that the July 3rd near miss. August 10th, that was at the time the new record setter of big blackouts. I've got a couple slides on that. 98 was a storm that had passed through and overwhelmed the system. By the time the N-1 happened, another set of events happened, and I won't get into the details of why it's interesting. It had to do with some restoration issues. And then 2003, it set a new record. I've got some slides on that. And then the most recent one is the 2011 one down in San Diego. Now you might notice that there's a lot of things not on this list. So what makes this list for me is this is when we have a failure of the transmission grid to maintain its stability and its reliability based on the engineering principles. I'm not including things like Katrina or Sandy or things like that come in and just wipe out infrastructure. And people are out of power because the infrastructure is wiped out, and you can't restore them until you rebuild the infrastructure. That's not an engineering failure in my mind. I guess you can argue how robust the infrastructure should be to natural disasters and things like that. But this is when you have a set of events that sort of cascades and goes out of control. And so these are things that can be fixed with kind of a focus on reliability projects and technology. All right, so the August 10th, 96. And I don't have a lot of time to spend on these, so I'll just go really, really fast. But the Northwest is a real big hydro area. About 70% of our generation in the Northwest is hydroelectric. And so we live and die based on how much snow is in the mountains in the previous winter. So we have a big spring runoff. And that particular year, we had a really great hydro year. That particular day, we had a hot day in California. California wanted our power, and we were happy to sell it to them. On that particular day, we had some utilities up around Portland and Seattle there, kind of where those yellow arrows are, take some things out of maintenance, take things out of service for maintenance. The problem is they didn't coordinate with each other. Neighboring utilities didn't say, hey, since you're taking that key thing service for maintenance today, I'm going to defer mine until next week. They didn't do that coordination. So a couple of things were done at the same time. The yellow arrows show where the power kind of had to reroute around some infrastructure was out of service. So the utility was sort of stressed, and it was an unusual pattern. Doesn't really show up in the blackout report, but another interesting thing that happened on that day is we were doing a fish flush to facilitate the migration of salmon to the ocean. So the migrating salmon, they swim upstream when they're adults, but when they're juveniles, they swim downstream. And the dams along the rivers kind of block their migration. And so to help the survival rates, we were running a lot of water through the spill gates, not the electrical generators. Well, that particular part of the grid where the yellow arrows are is where some of those big dams were. Well, they weren't generating. The generation was up in Canada. So the generation was coming through that area, there wasn't a lot of local generation, so the voltage support was weak in that space. So the voltage was going down. At 34203, we lost a 500 kV line. Overhead transmission lines are not insulated. The aluminum that you see in the air requires air around it. That's why they're strung from the steel towers by those insulator strings. It requires air to insulate the overhead transmission lines. If you have anything that gets too close to those wires, like trees growing up in the right-of-way, if it gets close enough, doesn't have to touch. If it gets close enough, it'll draw a short circuit, and it'll arc, and then the protective relays at either end of that line will sense that and trip that line and de-energize it. If you have one event, like a lightning strike or something like that, they have automatic reclosers, so you can bring that line back in. Sometimes you'll see the lights blink. That's somebody's line that reclosed. It tripped, cleared the fault, reclosed. That's a transient fault. But if you have a tree there, it's just going to draw the arc again, so it's going to have to lock that out, and then that line will be out of service. A heavily loaded line, the more current it carries, it heats up. The current flowing through the wire heats the wire and it sags. So a heavily loaded line will sag into those trees underneath it. That particular line tripped. It was within its rating. The trees were just too tall. And then about 5 minutes later, we lost another 345 kV line, and then the system went unstable. These are growing oscillations here, electromechanical oscillations. This is a power plant in the area that tripped all 14 units of the McNary generation. So this is showing the megawatts on some key dams around the area. And then the Malin Mountain is a transmission line between Oregon and California. And you can clearly see the oscillation, the growing oscillation there. So this is the really big takeaway from that particular outage. People were kind of surprised the day of the outage because they thought the system was within its operating limits. And when the system collapsed, people went back and said, well, we're within the limits that the computer model said, the system should have been safe. Well, the problem is then after, this is during the blackout investigation, we ran a computer model of this is the sequence of events, that's the blue line, and then compared it with, okay, what really happened? That's the red line. Well, your computer model predicted no blackout. So if you follow the computer model, sure, there's not going to be a problem. So this led to a big effort on model validation. So using system events, stage system tests, gather information, and then compare that to your computer models to make sure that you've got the right sort of physics captured, and you're modeling the damping of all these oscillations. We knew about these oscillations, we just didn't have the damping in there correct. The 0.3 hertz north-south oscillation was overestimated in terms of its damping. So that was the big one. This led to a whole bunch of DOE money and made me happy. So the next one I want to talk about is the 2003 blackout. And this is the current record setter for North American grids. If you want records in terms of total number of people affected, I think India now has that distinction with big blackouts. But this was a doozy for us. And so I'll spend some time talking about the sequence of events and what we learned out of this one. Oh, and by the way, if you ever see a picture, a satellite picture that looks like a big chunk taken out of the Northeast, that's a Photoshop hoax. That's the actual satellite picture there. So if you study it, you can see that there's loads that are not there, but it's not as dramatic as the Photoshop hoax. So we had the blackout investigation. I helped serve on the electric system working group. That was investigating the cause of the cascading failure, electrical failure. Why did this happen? The nuclear working group, there's 16 nuclear plants that tripped, and so they wanted to look at how well did they perform, did they do all the things that they should have. And then the security working group, so the electric one was headed by DOE and the US government, the nuclear one was NRC, and then the security working group was headed by the DHS. And a lot of people don't realize this, but the day after the blackout, Al-Qaeda took credit for it. And so we had to run that to ground to make sure, is that true, not true? Did anybody else hack into there? So that was really a computer security issue. And that got kind of interesting because 2 of the 4 root causes had computer failures as part of them. So that was worth investigating to make sure that there wasn't either malware or some sort of hack that took place there. I'm going to refer to a lot of organizations. This is a map that sort of shows who's who. The colors are the different utilities. The hash marks are the reliability coordinators. So the utilities I might mention are First Energy, American Electric Power, and you can kind of see one of the things that this picture reinforces for me is that the service territory boundaries between these utilities, it's often kind of convoluted, or often very convoluted. And so you can see the boundary between AEP and First Energy is you know, kind of a very weird shape. And then the hashes, that's PJM being the reliability coordinator, and the polka dot sets MISO being the reliability coordinator. So you also have a very jagged boundary between them in that same area, because First Energy belonged to MISO and AEP belonged to PJM. It was an interesting day. There was a lot of things happening on that day, some planned outages, things were out of service. The operators were worried about voltages. Frequency was kind of similar or common within range. It was warm. It was a warm day in August, but not record setting. This is a plot of, let's see, the bottom number is a normal daily high for August, and the top number is a record high for August, and the middle number is what the high was on that day. So everything was kind of above normal, but no records were being set. This is a contour plot of the voltages, so some voltages that most people would consider relatively low in the area of Ohio. This is a plot of frequency. It's well within normal range, you know, between 60.05 and 59.95 is very, very typical variation of frequency. One of the things that is nice that got captured on this slide, it's a piece of trivia, but notice that the scheduled frequency went from 60 to 59.8 at noon. If you have a clock that plugs into the wall, it keeps time by counting how many cycles that 60 hertz grid runs. And if the grid is off, the utility companies will offset that to get that clock so it stays accurate. And they still do that. And then I made some comment about, well, the new quartz clocks here, the digital clocks, don't do that. Well, then I was corrected. They actually do. If it's a battery clock, it's run off a quartz oscillator. But even if you went out to the store today and bought a plug-in digital clock, it still uses the grid to correct for the frequency, for the keep time. Okay, so the first thing of relative interest that happened on that day was a power plant on Lake Erie tripped. The reason it tripped, it was a failure in the exciter system. So the voltages were low, so they're trying to get the voltage increased by putting out more reactive power. And then that's managed through the exciter system. And that went offline, and then it tripped the plant. So we lost 600 megawatts, and we lost a critical voltage support there in that area. So that's near Cleveland. Second thing that happened just off my map here on the bottom of the map is a line tripped off. This wasn't interesting from an electrical standpoint, but what it did do is it screwed up the computer model called the contingency analysis. It's driven by the state estimator at the Midwest ISO, Independent System Operator. And they're the organization that oversees the First Energy utility company. So they weren't getting good information because of this line that tripped. The problem was the telemetry wasn't correct. They thought the line was in service when the line was really out of service. The computer model didn't match the rest of the telemetry, and tracking down that process took a while. The next big thing that happened is there's a computer failure at the First Energy utility company up in northern Ohio, and it failed. It went to backup. It failed. The control room guys called in tech support. They rebooted it. They got it working again. They thought everything was working properly, but unknown to anybody, the alarm processor was still in a failed state. The alarm processor takes all the data from what's going on in the grid and presents that to the operator in a way that they can kind of have situational awareness of these are the things that are happening and things I need to take action on. And it sort of sorts things based on importance. So it's an important tool. But when it's failed, that's bad because then the operators don't know what's going on. When it's failed and the operators don't realize it's failed, that's really bad because then things are happening and they don't know that they should be worried. This is just a screenshot of what these things look like. This is not theirs, by the way. I just grabbed a screenshot. All right, this is the most important first electrical event. This is a 345,000 volt line that tripped in northern Ohio. It tripped due to being too close to a tree. So this is the picture of the fault current that caused it to trip. It was within its rating, so the tree was too tall. And then about 30 minutes later, 3:32 in the afternoon, we lost another 345 kV line. Now the way these maps work is the thing in yellow is the other line that I showed. So if it's in yellow, it's from previous slides, and if it's in red, that's the one on this slide. So right next door, another 345 kV line tripped. It was also a tree trip. Tree contact got too close. Now this is a picture taken on that day of that line. They were out working on it. And what was very, very interesting to us in the investigation, see if my laser point works, is that limb is dead. This isn't the first time that this line had tripped due to that tree. So, and the crew actually witnessed it fall on that afternoon. And I don't want to disparage any interns here, because I might be surrounded by folks that intern places, but it was fascinating in the transcripts. An intern at First Energy called into the control center saying, hey, I just saw a line fault out. You might want to know about that. Now remember, the operator, their alarm processor wasn't working. The data was going into the computer screen, but their alarm processor weren't working. So if they pulled up the right screen, they would have seen that the line was out. Intern said, hey, it was on the Juniper Star line. The operator brought up the Juniper Star line, saw that it had voltage, saw it was flowing power. Okay, so he assumed either the intern's giving him weird information or that the line reclosed and was running again. If the intern had said, Hannah Juniper line, the correct line, the operator would have pulled that up, saw that that line was out of service, no voltage, no flow, and might have said, hey, why don't I have this in my alarm processor? What else is going on? And they might have taken a different course of action. So that's not in the blackout report, by the way. At least I don't think it is. So the next line that tripped, this is also a line within its rating, was at 341. And then another line that rated, this was overloaded, but it was also tree contact. If it's overloaded, you can't blame vegetation management. And then this line at 405 was the Samastar line, and this was a critical event. This is the first line that tripped, not because of a fault, a short circuit, because of the getting too close to the trees, actually drawing a short circuit. This is a line that got so crazily loaded up because all of the lines around it had tripped. The power is still flowing through the grid. The electricity doesn't flow through the power lines based on what the utilities tell it to. The electricity flows based on the laws of physics, right? The path of least resistance. And you have this big load center, Cleveland up there, drawing power through the network, and all of these lines are tripping, so more power is flowing through the other lines. This particular line tripped because its protective relay thought that it was faulted because a crazy amount of current was going through it, and it was tricked into tripping. That's the beginning of a uncontrolled cascading failure. And at this point in time, the sequence of events shifts because now once you lose one line that way, you're going to lose other lines that way. It's a domino effect at that point. And this shows all the way back from noon getting up to that point. And so what this shows, this plot, is the flow on all of these lines I'm talking about. And you can see right here about shortly after 1 o'clock, that's the effect of that power plant that tripped I talked about. So the power plant tripped, so more flow through the lines to make up for it. And then when you start losing the lines, so this is the first one, that power has to be picked up by the other lines, right? And so then you lose that one, and they go up to there, and so on and so forth. And so it's kind of a domino effect, but it really was the Samastar line that tripped due to protective relay action. And this is what the voltage was doing at the whole time. 90% nominal on the transmission line is considered very low. That's the point, the relay setting point that it tripped. And then I'm just going to breeze through several slides here, but this is sort of how the cascade continued on through the next 5 minutes. And then once all those lines tripped, Detroit and Toronto are hanging onto the grid, but they have to be fed around the other way, around Lake Erie. And that took out all these lines until eventually that was separated. And then sort of this picture isn't very good, but this shows the footprint of the blackout. So it was pretty much everything northeast of that line, with some exceptions. Upstate New York kind of rode through it okay, but I don't have time to get into this plot, but this is frequency measurements taken from different parts of New York State, and it shows the difference between upstate New York and the part of New York that includes New York City. This is the part of New York that includes New York City, and this part of the curve is when all of that under frequency load shedding was exhausted. Right? It fired all of its under-frequency load shed, but that wasn't enough to save the system, and it eventually collapsed. this part of the system survived with some huge excursions, 63 hertz. I've never personally seen excursions that big. These are the power plants that tripped off. Boom, boom, boom. All right, so you're wanting to know what caused all this. So root cause number one is the utility didn't really do a comprehensive job of understanding the limitations of the system. This is subtitled by me, lack of institutional memory. There were some studies done back in the 80s by the predecessor utilities saying, hey, if you operate the grid in such a way, it could set up a sequence of events that could cause this kind of thing that could happen on that day. So to prevent that, maintain voltages at such and such places be above certain limits, and they had forgotten about those previous engineering work. Number two, lack of situational awareness, and this is directly caused by that alarm processor I keep talking about. So the control room operators didn't know what was happening on their system. And remember that picture I showed of California ISO, and they had that giant display board on the wall that showed the status of their system? At the time, First Energy did not have a status board like that. They relied on the operator's workstation to, they had to be screened into the right screen to see what was going on. Root cause number three was inadequate vegetation management. One thing that we looked at to investigate was on that particular day there's very little wind, and the utility industry standard practice is to assume 2 feet per second of wind speed to cool the lines, the overhead lines. And so when you rate a transmission line, you assume some wind. 2 feet per second is roughly about 5 miles an hour. So you assume a little bit of breeze to cool the line. And at that time when all these lines were tripping, the Akron airport was reporting 0 knots of wind. And so we thought, well, maybe our whole practice of rating lines is not right. But we ran the numbers, and it was just a few feet of difference between 0 and 5 miles an hour. And then I love this picture. This isn't any of the lines I talked about. This is an earlier event that happened on that day. And in fact, MISO was preoccupied by this one. They thought the grid was going to collapse at noon because of this line. But it didn't, and they got that fixed. But this shows a nice before and after picture of, so after the blackout hits the news, you can get more leverage with the landowner to say, yes, we really need to go in there and do vegetation management. And then root cause number four was the reliability coordinator. MISO wasn't effectively overseeing what, that's essentially their job, is to manage the utilities under them to make sure that reliability is preserved. So, and then a lot of things that people thought it was caused by that the investigation proved it wasn't, including Canada. The day of the blackout, there's a lot of finger pointing. U.S. said, oh, it started in Canada. And then when it proved that it didn't, we had to apologize. Fortunately for me, I never got on record of saying anything that I couldn't stand behind, so that was luck on my part. So so my comment about resilience. So now thinking about these events that I talked about, so you can reduce the magnitude of the event, you can reduce the duration of the event. So one of the things that people are thinking about in terms of grid resilience is adaptive islanding. So if the grid starts to fall apart, can you have pre-planned ways to split it up into smaller sections, let it recover, and then bring it back together? That's a very classic example of reducing the magnitude of the event. Reducing the duration of the event is, for example, making sure that there's no physical damage that takes place. And so then you can bring it back much quicker. So the 2003 blackout, even though it affected 50 million people, all the customers were brought back online within a few days. The lingering outages were, they asked some industrial plants to stay off a little bit longer. Industrial customers stay off a little bit longer until they can get the nuclear plants restarted and get them served. But residential customers, even in New York City, were back online by the evening of the next day. And that's not possible if there's physical damage. And then the key thing is think of these events as all hazard events. Doesn't matter if it's a weather induced, an adversary induced, or just equipment failure or anything else. But think of these events as all hazards, but also your resilience plan or strategy should be able to prevent against unenvisioned events. So it's not so much just mapping out all the scenarios you can think of and making sure it hits all those, but having these concepts, so even if it's an unenvisioned event, your resilience strategy still will work. Okay, so how does this relate to the smart grid? Well, the smart grid, and I mentioned this earlier today, you can probably take 10 engineers and ask them, define the smart grid, and you'd probably get 10 different answers. I feel pretty confident about this definition because I got this from DOE, the DOE system report, which of course I helped write, but that's okay. So the smart grid is really, it's using information technology to enable a more effective delivery infrastructure. And so a lot of people are thinking about it in terms of better end-use management, demand response, end-use load control, smart metering, automatic metering infrastructure and things like that, but also can apply to transmission level things as well. But it's really things that are enabled by improved use of information technology. And if you think about how other parts of our society are being transformed by digital and information technology, we just want to continue to apply that to the grid. And the other thing is, I should have put in my slide smarter grid. It's not that the grid before now is dumb and we're going to make it smart. It's a process where we're adding on more intelligence into the system. But one of the key things that we focus on at P&L is harnessing more on the demand side. So traditionally, the utilities do much more of their control on the supply side. They manage their power plants. They can adjust the output of their power plants. They can, manage their delivery infrastructure, and then they try to project what the load's going to be. And the load control process is very rudimentary in a lot of utilities. We believe that bringing in things like interruptible load and making those interruptible load incentivized to run when it's maybe off-peak or things like that, or maybe not even just peak and off-peak, but maybe if there's an emergency on the grid, maybe getting some of your interruptible load off the grid at that point in time. So kind of a real-time situational awareness from the demand side, and then really get this infrastructure to operate more seamlessly between supply and demand. We think there's a lot of benefit there. We also think that if you put more of this intelligence in the grid, you can use that data to enhance situational awareness, better understand what the real state of the grid is, and then use that information to help when you have a weather event, or maybe even if you have like a terrorist attack or something like that. You might be in a better situation if you have more data that you can work with and more flexibility in terms of managing your infrastructure. There's a lot of push to get more renewable resources onto the grid, like wind and solar. Wind and solar are variable generation. I have intermittent on my slide here, but it depends on who your customer is. Some people hate that term as it relates to renewables. They say it's not intermittent, it's variable. Well, I've seen plots, it looks intermittent to me. But it's good because it's sustainable. If you use solar energy, you're not depleting our resources, right? So you need to work around the fact that it may not be there when you need it. And storage is available, but it's expensive, so it's not, maybe it's better to try to manage your portfolio of all your resources instead of discounting stuff. I also believe that when you do have an event, things like hurricanes or other types of major events, that if you have these smart grids deployed, that you can manage that better by maybe compartmentalize or islanding your system or managing it in smaller chunks. Already we've seen utilities make great strides with their customer notification process. Down in the DC area, I believe it was just last summer, they had, what was that called, that big storm that came through, derecho or whatever the thing is. I'm not thinking of the right word. But one of the utilities had deployed a very complete AMI in their service territory, and they had a very excellent outage management system that they're able to project to their customers. Here's how many customers we have out of service. Here's when, by zones, when you can expect your power to be back. And customers really like that information and that feedback. The utility next to them was still working the old way, like, call us and let us know if you're out, and we're not going to call you, You just wait for the truck to show up. And they're not so liking that. And it was, the regulators noticed that because these utilities are right next to each other. And one had very favorable outage management feedback from the customers, and one was very unfavorable. And so that's managing an event. And then some of these technologies may not even really require communications. This is a technology that we're working on where it senses the frequency on the grid and makes an autonomous decision based on that. So maybe load shedding, but before it gets so low that other things are happening. But communications for a lot of other things in the smart grid is central to the deployment. And so here's an important point that I want to get across today. So we're talking about the smart grid potentially helping with resilience because it's giving you more flexibility, more resources, more assets, more things that you can change in terms of your deployment strategy and your management strategy. But you're introducing a cyber layer, right? You're introducing information technology to manage your smart grid assets. So if you've introduced a single point of failure or an attack surface that wasn't there before, so if somebody can get in there like with a cyber attack and do something that looks like an n minus a lot, versus what the utilities are used to working with as n minus 1, then you've introduced a brittleness into the system that takes away from the resilience that you might have already had or works against the resilience that you're trying to improve upon. So it's very, very important, in my opinion, that as we deploy the cyber systems to manage and control these assets, that they don't have common mode of failures, that they don't have a place to introduce a widespread effect, and that the security is such that we're not introducing a brittleness to this, right? And so again, it's not, my main comment isn't so much, yeah, they have to be secure. The cyber security needs to be applied and deployed. But even if the adversary is willing to or able to thwart the security measures that you've put in place, through a attack scenario that you haven't envisioned, you don't want the underlying infrastructure to enable them to succeed with an attack that will have devastating consequences. So you want to compartmentalize that, make it such that their ability to carry out an attack is limited. One of the things that's challenging about this is that there's no common place as jurisdiction over these issues that we're talking about. So FERC and NERC, FERC is the Federal Energy Regulatory Commission, NERC is the North American Electric Reliability Corporation. So it's very complex because NERC includes Canada, but FERC is just US. FERC and NERC only apply to the bulk power system, 100 kV and above. Distribution utilities are regulated by the states, right? So there's 50 plus state regulators. Honestly, I don't know who regulates DC. I'm assuming they have their own regulator, but I don't know. So at least 51 probably distribution regulators. And a lot of these utilities then cross state boundaries. Like I think AEP serves 11 states. And so it's a very, very complicated regulatory framework. And then the technology is evolving at a very fast pace. So there's a lot going on here in this space. So I guess my point in all this is that we as technologists, people sort of coming up with these ideas and working to get them eventually deployed in the industry, need to sort of think ahead and think through these consequences and work through these problems, and don't rely on the regulators to make sure that the requirements are put in place that the implementers have to follow certain approaches. So I also can't resist throwing in a couple of slides on some of my pet projects. One of them is the North American Synchrophaser Initiative. This is an initiative joint between NERC and DOE to deploy and implement and utilize data from phaser measurement units. What a phaser measurement unit is it has a common time reference. So we use GPS as our common time reference. And that calculates the relative crest of these voltages at different parts of the grid. And so we can measure the relative phase angles between different parts of the network. The other advantage of this technology is it's high speed. Typical SCADA telemetry is about once every 4 seconds. Typical PMU telemetry is 30 samples per second. So some people use the analogy, it's like going from X-rays to MRIs, things like that. But the advantage or one of the advantages that we are thinking about in this is it allows wide area situational awareness of, so the dots, these blue dots that are shown on these maps, these are devices that are networked and shared with multiple utilities. So this isn't just people putting in stuff for their own use. This is putting in stuff for the benefit of the entire interconnection. So this is kind of a big deal to get a shared perspective in terms of what this infrastructure is doing. Now, Remember what I said earlier about introducing a single point of failure? The timing for all these, where's it all coming from? GPS. So we need to be careful. The applications are getting more sophisticated as we go. We're starting off with applications that are pretty easy, like visualization. We're moving towards applications that are more complicated and haven't been implemented yet, and that's wide area feedback control systems. Comments on the security. My main takeaway on the security of these is it depends on the application. What you do on what's required in the security depends on what you're using this data for. That's a very important point. And that applies to not just synchrophasers, it applies to everything else. And then my final slide, well, second to last slide, is we have a new initiative at PNNL called the Future Power Grid Initiative. So this is exploring next generation data and networks, modeling and simulation, and visualization decision support to sort of look forward and anticipate where things are going in the future and come up with some technologies to get us there. So with that, I am available for questions. Right here in front. Tell you first.
So about this N-1 compliance, I'm wondering, so if there's a failure, does the system then automatically update to N-1 because now N is decremented by 1 and needs to quickly make additional use?
Yeah, excellent question. So, so kind of behind that way that it's set up is that there's some, lack of a better word, inertia. I'm not using that term in engineering sense, but things kind of happen at a measured pace. And so the rule is that within 30 minutes you have to reassess where you're at and implement the next round of contingencies. And the 30 minutes isn't scientifically derived, it just somebody grabbed it out of the air and said, that sounds about right. And the idea there is that that's time for the organization to assess what happened, what they're, if they haven't recovered from that, and then get in place a next round of contingencies so that they're ready for the next one. And so that's open for debate whether that's the right number or not, but that's been done. The 98 one I had on my slide of best hits, that's where they had a storm going through an area and they lost a line, then they lost another line, then they lost another line. And it was, they weren't violating that 30-minute rule, but things were happening faster than that, and so it kind of got out of their control. Great question, though.
I was also wondering, so just like a very general thought, so as you're thinking about making the grid smarter, do you have to worry about sort of resisting the temptation of making the operator less smart? So if there is more decisions that are happening automatically, how do you incentivize the operator to nevertheless understand the basics and not just rely on like color?
That's another great question. So, and I'm going to borrow another industry to answer you. So in aviation, they're finding this a lot. There's an over dependency on autopilot, and then the pilots forget how to land the plane, right? And, so in the grid area, we are very, very interested in technologies to enhance decision support, for the operators. I don't see the operators going away, in terms of introducing technologies. We're not trying to eliminate the operators. But in reality, when you do a job task analysis of what they spend their day doing, there is a lot of things that they do that could be automated. But it's a balancing point because you don't want them to sort of get disconnected from the feel of what the grid should operate. And it's not directly answering your question, but it's kind of a funny story. So one utility replaced the printers in the control room. So who would think anything about that, right? Well, the operators immediately hated that because their old printers were these line printers, And so when they knew that crap was happening on their system, they would really pick up the tempo and they could hear it, right? And the new system was all digital or whatever, right? It was just putting stuff in a log and they could pull it up on their screen, but they couldn't hear anything. And so they lost this sort of tactile feedback of, oh, I better pay attention because something's happening. Because when the alarms would start coming in at a faster pace, that line printer would really start going to town and they could hear it. So it's not directly answering your question, but in that human factor space, there's a lot of issues that we don't fully understand, in terms of how to keep the operators engaged and that sort of thing. Now, one other comment, and I really emphasize this on the 2003 blackout, but there was an hour from 3:05 to about 4:05 that the system was not following the n-1, within its limits officially. Yet the grid, it took an hour for it to decay to the point where it went into uncontrolled cascading failure and finally collapsed. So in that hour, the operators in the control room did absolutely nothing but answer the phone and talk to people. They didn't push any buttons. They didn't do anything. They would have been more effective out getting coffee, right? Because nothing was done during that hour, right? So that gives you an idea of the, and again, it's not inertia in the classical rotating inertia sense, but there's some inertia in our grid, in terms of how fast it takes things to happen. Just probably because it's such a big grid and there's so many automated controls in it. So you had a question, sir.
Yeah, simple. Early on, you had a table that was sorted by date on the blackouts.
Yes.
It didn't look like they were becoming less frequent.
Yes, that is an astute observation. And that's something that we're worried about, right? And so as the system becomes, and then there's some really good research on this issue of, is this complex engineering system, when you measure the frequency of failure and the size of the failure, is it really following normal theory? There's a power law and the tail and all that stuff. And you can tell from my comments that's not my research area. And more, the big blackouts happen more frequently than they should per science, right? I mean, if you just look at the laws of, a normal engineered system and failure versus size, it should follow sort of a distribution. And our grid kind of doesn't. The bigger blackouts happen more frequently than they should. They are spaced about 10 years apart, And I'm always very careful to say that our reliability research is not going to prevent blackouts. We're just going to make them less likely. Yeah, but it's a great point, and getting to the root causes of that is an interesting challenge, right? Because I think there's a lot embedded in there in terms of how we restructured our industry, and then trying to squeeze more economy out of our infrastructure as well. So kind of a soft answer to your good question. Yes?
This is kind of, I guess, a naive attempt at a practical question, which is that I've heard that a lot of these renewable sources that are coming online in places that are highly populated, right? So they're not super well connected to these networks. What's your sense of how easy it is to build new big-time parts of the grid? Because I've had a sense that this hasn't really been done in 15 years.
Yes, that's an excellent question. A lot of people are losing sleep over this. So the problem with the grid, and one of the reasons why we're so interested in this technology is to squeeze more out of what we've got, because building new lines is incredibly difficult. It's even more difficult now. In the old days, when you had to build a line, you could justify it saying, well, we've got people that we've got to serve here, and so we got to build this line. Otherwise there'll be people in the dark, right? And so the people who the line was going through could kind of feel that. It's like, okay, yeah, we get that public benefit. But if it's to tap in a generation source, and you have ultimately behind it somebody that's trying to develop a wind farm and then make a profit from that, and wheel the power through the third party that's in the middle that just has to put up with this line going through no benefit of them, that's very challenging, right? So building infrastructure, particularly when it's hard to sort of directly connect it to a public good and it's more of a profit motive, is very difficult. Now, we've all heard of the term NIMBY, right? Not in my backyard. Who's heard the term banana? All right, build absolutely nothing near anybody, right? So that's what it's come to with these transmission line siting projects. It's extraordinarily difficult to add transmission lines. And you're quite right. A lot of our wind resources, people have coined the term we're the Saudi Arabia of wind in the U.S., right? But it's all in North Dakota. And so we have to get it out of there. And so people are considering different options. If you're really interested in moving lots of power over short distances, you can go with DC transmission lines. And one of my maps here shows that really well. So there's, they call it high voltage DC, HVDC. And so that's what people are thinking about for getting the power out of the middle of the country. Right there. So these two red lines up there, those are DC lines. And the north-south one, this one here, that's what we call the Pacific DC intertie. It was first energized in 1972 and currently is rated for 3,100 megawatts. That's a lot of power through one line. But when you look at it, it's a very compact line. It's just 2 wires. It doesn't take up much right of way. And even though it's plus or minus 500,000 volts, so 1 million volts between the wires, it's fairly compact. And so people are thinking about, well, we just build some DC lines, getting the wind out. But that's a challenge. These are expensive. It's an expensive infrastructure and extraordinarily difficult to site. One of the benefits that people are citing for offshore wind is they think they can bring the power in to the load center without any arguments from landowners. So that's one of the big pushes now for DOE's wind program is to do some offshore wind siting. And so there's been some corridors designated by the government. These are areas that are ready for offshore wind development, and all they got to do is get a developer to build it and bring it in, and they're going to use DC to get it there. But the advantage then is you bring it right into the load center because the big cities are along the coast. So, but that question is far from being solved. I don't want to imply that that's solved because that's still a big problem, and we're continually trying to squeeze more power out of our existing infrastructure with advanced technology. So.
I was curious about the example where the real system had an uncontrolled oscillation and the simulation didn't. Was the modeling problem inaccurate parameters, or was it that the real system had more complexity that wasn't in the model at all?
Is both. So the phenomenon here that is happening is well known. Power engineers know all about this. It's an electromechanical oscillation. It happens in grids all around the world. What it is it's the, I guess I'll use an analogy to describe the phenomenon. If you think of the power grid as the transmission lines as springs, and you think of the generators, the rotating inertia as mass, then in steady state conditions, everything's nice and stable. You can put those springs under more tension, right? You get everything stable. But then if you perturb the system, go from one operating state to the other, things will oscillate as it goes to the new state. If you write out the differential equations for that mass spring system, and you write out the differential equations for rotating generators connected to electric transmission lines, it's the same equation. So the analogy kind of holds mathematically. But in this particular case, it was the generators in the northern part of the system oscillating against the generators in the southern part of the system. Is a 0.3 hertz oscillation. This oscillation was first observed in the 70s when they built an intertie between the north and the south. It shows up more prominently in systems that are long and stringy than systems that are more meshed. And so this does exist in Eastern interconnection, but not as prominent as the Western interconnection. But grids like Australia that are all along the coast, they have this in spades, right? And Brazil has this because they have big generators that are far away from their load center. So on this particular day, the models had all the, you could actually see this oscillation in there, but it was very well damped. And so what they had assumed, so it's kind of a two-part to your answer there. They had made some assumptions in the model about technology that's called power system stabilizer, PSS, that are installed on the generators that dampen out these oscillations. More of those were assumed to be in service than were actually in service. Some of the gains were different in the model than in real life. Right? So after the blackout, they had to do a lot of generator testing to find out, okay, really what are these plants doing? And then they had to create some increased standards in terms of here's the requirements that you have to have in order to be interconnected to the system. But they also found that one of the things that they weren't modeling very completely was the low voltage and the load side. So motors weren't being modeled. They were just, certain number of megawatts at a substation, but it wasn't being modeled as motor load. Well, that influences these dynamics as well because the motors are rotating inertia, right? So if you model something just as okay, I'm taking so many megawatts at this point versus, okay, this is how many megawatts is going into resistive load, inductive load, constant impedance load, and then this is your motor load, and then you put in some parameters in that, include that in your model, you get much better match. So it's kind of a whole bunch of things that go into that. Great question. And this by the way, is never a completely solved problem. If you, I mean, we're still working on model validation and testing the models against real life, and we're always learning things and improving the models. But I will say that compared to today, compared to then, in the Western interconnection, it's way better. Eastern interconnection, I'm not so sure, because you guys don't see as many of these oscillatory events. And so I've seen some oscillations that have shown up in the PMU data that aren't in the models. And so maybe you've got one of these coming around, to your question about what's going to happen next, right? Maybe this is lurking in the Eastern interconnection models. But I'm not going to, well, I said it, but I'm not going to state that categorically. I just kind of amusing, I guess. Well, I'll let somebody else have a crack, just because you already had two.
Just a thought about this sort of frequency, every 10 years it's not going down. People have documented bridge failures, and we've been building bridges since the Romans, and they still haven't. And part of the explanation, and it happens every 40 years, a catastrophic bridge failure. And the hypothesis is that people get too good at optimizing, so they'll have some model, and they'll say, I can make more money if I reduce the material. And then something happens where that slack capacity is gone, and there's some physical effect that wasn't in the model, and now it becomes significant. And so I wonder if there's a similar thing here. You had those 4 priorities, right?
Right.
And the last one is making money. So if I'm a manager, I'd say, okay, we got the first 3 pretty well modeled. Let's go after 4.
Right.
And then you don't have any margin.
And each year that you're successful squeezing out more profit, you might get, each year you're going to cut a little bit thinner and cut a little bit thinner. Yeah. No, I think there's a lot to that. And when you look through this list, there's a lot of commonalities across this list. One of the things that was sort of fascinating to me is on the investigation team is in 2003, we saw all these trees that were causing outages in one particular utility. And the lines weren't overloaded. It's the trees were the lines were within their ratings, and they were tripping anyway because of these trees. And so FERC wanted to throw the book at them. Okay, so what rule were they breaking? And nobody could find any standard or rule that says you got to cut your trees to a certain distance from the line. It didn't exist. So NERC had to create, after 2003, what they call a vegetation management standard. So that's an example, right? So and trees show up in a lot of previous examples, but no, that's an interesting perspective, and a lot of people, and again, there's a lot of outages not on this list, right? That create interesting things to think about. There's one in Florida. I didn't include it because it didn't cascade out of the area. So thinking about the frequency of the outages and what, I went through the root causes of that particular one, but there's sort of super root causes, right, in terms of how the industry is regulated and how people are managed. And one time I heard a vice president of operations at Tennessee Valley Authority sort of joke that the lack of blackouts in his area, correlated to his tenure. So he was still there because there hadn't been any blackouts in his area.
That's the concept.
Oh, yeah. Well, so I guess on that note, I'd like to speak here again.